Assalamualaikum warahmatullahi wabarakatuh and greetings everyone. Today, Group 4 will present to you the working principle of thermodynamics in a refrigerator. And this is the table of content that we will cover in this video, so stay tuned. And I will introduce all of the 4 group members. Firstly, me, Ni Ahmad Nafahmi Beroslan, and then Nur Sabrina Afifah, Aina Nasuha, and Aina Masara. So firstly, I'm going to do a little bit of introduction on how does a working principle of thermodynamics works in a refrigerator. A refrigerator is an open system that expels heat from a closed space to a warmer area. By doing so, it will decreases the temperature and allow a food and other items to remain at a cool temperature. Refrigerators appear to violate the second law of thermodynamics, but the key reason they do not is because of the work needed as input to the system. They are essentially heat pump, but instead of using a heat pump to heat a region, it used as a cooler to the region. According to the second law of thermodynamics, heat will always move from a hotter region to a colder region, and it will never go the other way around. So now we're gonna move to the refrigerator system and see how it works. Firstly, work is input in which compress a coolant, increasing its temperature above the room's temperature. Heat flows from this coolant to the air in the room, reducing the temperature of the coolant, and then the coolant will expand and it cools down below the temperature inside the refrigerator. And lastly, the heat flows from refrigerator to the coolant, decreasing the temperature inside. And we can see the illustration here. It will give you a little bit detail on how the refrigerator system works. Now we move to the statements of the second law of thermodynamics related to the refrigerator. The first one is waste heat statement, also known as Clause's statement. It is said that heat cannot be converted entirely to mechanical energy. The second one is refrigeration statement, also known as Kelvin-Planck statement. It is said that heat will always flow spontaneously from hotter substance to colder ones. The last one is disorder statement, which combines both of the Clauses and the Kelvin-Planck statement. It said that the entropy of a closed system can never decrease. Now I'm gonna pass this presentation to Nurul Sabrina to explain more on the Clauses statement.
In Clause's statement, it is impossible to construct a device that operates in a cycle and produce no effect other than the transfer body to a higher temperature. For Kelvin-Planck's statement, he said it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce the net amount of work. Equivalence of these two statements, which are the Kelvin-Planck and the Clauses statement, are equivalent in their consequences. An interior statement can be used as the expression of the second law of thermodynamics. Any device that violates the Kelvin-Planck statement also violates the Clausius statements and vice versa. As you can see here, this is schematic diagram that represent the Kelvin-Planck statement at the left side and at the right side for Clausius statement. Schematic diagram.
Assalamualaikum and hi, my name is Aina Nasuha binti Jamal and I'm going to present about the reverse Carnot cycle. Reversing the Carnot cycle thus reverse the directions of heat and work interactions. A refrigerator that operates on the reverse Carnot cycle is called a Carnot refrigerator. Carnot cycle is a totally reversible cycle which consists of two reversible isothermal processes and two isentropic processes. It has the maximum efficiency for a given temperature limit. Since it is a reversible cycle, all four processes can be reversed. This will reverse the direction of heat and work interactions, therefore producing a refrigeration cycle. The cycle consists of process 1 to 2, isothermal heat transfer from cold medium to refrigerant, evaporator, 2 to 3, isotropic, reversible adiabatic compression, 3 to 4, isothermal heat rejection, condenser, and 4 to 1, isentropic expansion. The reverse Carnot cycle is the most efficient refrigeration cycle operating between two specified temperature levels. It sets the highest theoretical COP. The coefficient of performance for Carnot refrigerators are 1 over TH over TL minus 1. So that's all from me, and I will pass it to my friend Aina Maisara binti Muhammad.
This is pH diagram for ideal refrigeration cycle. There are 4 processes of the ideal vapor compression refrigeration cycle. For process 1 until 2, horizontal lines are drawn across the refrigeration's pressure enthalpy diagram for the suction and discharge pressures. Then, the incoming temperature of the compressor is determined by the leaving temperature of the evaporator. The compressor then increases the pressure of the refrigerant up to discharge pressure. Compression occurs at constant entropy, also known as isentropic compression. For process 2 until 3, the refrigerant entering the condenser is now a high pressure refrigerant gas. The condenser is shown on the pressure enthalpy diagram as a horizontal line. The horizontal line is a line of a constant pressure corresponding to the discharge pressure of the compressor. For 3 until 4, the expansion valve is characterized by the suction and discharge pressure. Horizontal lines are again drawn on the refrigerant pressure enthalpy diagram. The input condition of the expansion valve is determined by the condenser output condition. The expansion valve expands the high pressure refrigerant gas adiabatically to a low pressure liquid vapor refrigerant mixture. Adiabatic expansion indicates that there is no change in enthalpy and characterized by a downward vertical line as shown on the below graph. This moves from the liquid phase of the graph to the vapor-liquid mixture region. For process 4 until 1, the refrigerant entering the evaporator is a cold, partial liquid vapor mixture. As the evaporator transfers heat to the refrigerant, there is no gain in temperature since all that heat is used to convert the remaining liquid to gas. In an ideal evaporator, there is just enough heat transfer to convert all the liquid to gas and nothing more. If additional heat were to added to the 100 refrigerant, then the heat will be used to increase the temperature, and it is this increase in temperature that is called superheat. This is the graph for the actual vapor compression cycle on the left side, and the right side is the diagram for the actual vapor compression cycle. This is the TS diagram for the ideal vapor compression refrigeration cycle. For process 1 until 2, there is a isentropic compression of the refrigerant from state 1 to the condenser pressure at state 2. For the process 2 until 3, heat transfer from the refrigerant as it flows at a constant pressure through the condenser. The refrigerant exists as a liquid at state 3. Process 3 until 4, throttling process from state 3 to a two-phase liquid vapor mixture at state 4. So, the last one is the process from 4 to 1 is heat transfer to the refrigerant as it flows at constant pressure through the evaporator to complete the cycle.
For the conclusion part, the refrigeration cycle, sometimes called the heat pump cycle, is a means of routing heat away from the area you want to cool. This is accomplished by manipulating the pressure of the working refrigerant, which are air, water, synthetic refrigerant, etc., through a cycle of compression and expansion.
So these are all of the references that we have been using while doing the assignment. And you guys can go to the website and check if you want further information about the refrigerator or heat pumpers. And now we have reached at the end of our presentation. Thank you for listening to this presentation, and I hope to see you guys again. Bye.